Hi all, welcome back to Ashkemi once again. So today I've come up with the part 12th of the question paper discussion that we were so far discussing. For those who have not gone through the previous video, I created a playlist in the channel and I have given the link of the same in the iCard above. So anybody, those who are interested can go through the previous videos. And apart from that, I'm getting many inquiries regarding the online coaching classes for Kerala Kpsc exam based on chemistry. So I would like to mention you that I'm starting a class in the month of May. And if anybody is interested to join the class, you can just give me a message in the WhatsApp number provided in the description box, and I'll be responding to it according to my convenience, and I can give all the details. It will be a very useful class because I cannot complete all the portion as YouTube videos. That is a more interactive type of class, which is a live class based coaching, so will be more useful for you. And so without wasting much time, let's get started. So the first question of the video is question number 38 of the question paper, which is about a portion in organic chemistry which is known as electrophile. So you are asked to find out the compound that is not an electrophile. So for that we have to understand what is an electrophile is. Okay. So an electrophile is actually a species that is electron deficient or electron loving. That is, since it is electron deficient, it will be having an affinity towards electron. So it have a tendency to get attracted to the area or attracted to the species which is having more electron. And it is generally represented using the symbol E+. Okay, so the most important criteria for a compound to be an electrophile is that it should be electron deficient. Now we'll consider each examples one by one. First, we'll consider methane. So when you analyze the structure of methane, it is having a tetrahedral structure, right? So when you look at all the atoms, that is, there are two different types of atom that is present in methane. One is carbon atom and the other one is hydrogen atom. So if you consider carbon atom, around carbon atom there are 8 electrons, and for each hydrogen there are 2 electrons. So it satisfies the octet and it is stable. So definitely methane is not electron deficient. Therefore we can rule out the possibility for methane to act as an electrophile. So most probably this will be the answer. Now we have to have a look at the other options as well. The second option is SO3. Now when you look at the structure of SO3, you can actually find out the structure of SO3 using a trick that I've already discussed in one of my video in the channel. You can just go through. I'll give the link of the same in the iCard above. So when you calculate the hybridization and structure of SO3, it is having a trigonal planar structure. And now if you count the number of electrons surrounding sulfur atom, it is only 6 electrons. Okay, so it is having only 6 electrons surrounding sulfur. Therefore, the sulfur is electron deficient. Therefore, SO3 molecule, it can act as an electrophile. Now coming to the third option is bromonium ion, that is Br+. So we have usually gone through Br- ion, that is bromide ion. This is the ion that we usually have. But this is a negatively charged species, probably acting as a nucleophile. But here it is having a positive charge. This means that it is having 1 electron less than that required for an octet configuration. Okay, so in order to satisfy the octet configuration, it requires 1 more electron. Therefore, bromonium ion or Br+ can also act as a electrophile. So usually electrophiles will be either neutral molecule like SO3 or will be positively charged. Now coming to the last option, that is BF3. When you consider the structure of BF3, again it is having a trigonal planar structure. Here also, when you look at the number of electrons around boron, it is having only 6 electrons. That is, it is also electron deficient. And BF3 is an important example for a Lewis acid. Most probably, Lewis acids act as electrophile. Therefore, BF3 is also acting as an electrophile. So, the odd one out in these options are methane, which is a stable molecule. So, it cannot act as an electrophile. Okay, that's all for this question. Now, we'll have the second question for this video, which is about homolytic fission. That is, homolytic fission for generation of free radical is favored most in the bond. So you are provided with 4 different bonds, and out of which will be undergoing homolytic fission easily. That is, normally when you have a homolytic fission, it leads to the formation of free radicals. So which bond actually favors the formation of free radical by homolytic fission. So when you consider the bond cleavage in organic chemistry, there are 2 different types of cleavage. Either you can have a homolytic cleavage or you can have a heterolytic cleavage. Suppose you are having 2 atoms that are joined by a bond. There are 2 different types of cleavage that is possible. Either this atom, the bond can cleave in such a manner that one of the atom is getting both the bonded pair of electron and the other one is losing. So this is one of the possibility that you can have. This actually represents a heterolytic cleavage in which both the bonded atoms are not getting the equal share. There is unequal distribution of the bonded electron between the 2 atoms. Now we'll consider the second case where the bond can break in or cleave in such a manner that both the shared atoms or both the bonded atoms are getting an equal share. That is A dot plus A dot. So in this case, you are getting either a cation or an anion. That is, in the case of heterolytic cleavage, you are getting a cation or an anion. But in the case of homolytic fission, this actually represents the homolytic fission. In the case of homolytic fission, you are getting a species which are known as free radicals, okay, because they have unpaired number of electrons. The dot actually represents the unpaired electron. Okay, so this is what we are getting. So there are 2 different types of cleavage. But the importance of this homolytic cleavage is that it always takes place in presence of light. That is, you will be getting this type of cleavage in presence of light. That is one of the important factor. And another important factor is that you can actually find such a cleavage only in the case of homonuclear diatomic molecule. That is, whenever you are having both the bonded atom the same, only in this case you can get a homolytic cleavage, because it is a cleavage that produces the equal cleave in such a manner that both the atoms give the equal share of electron. This is not possible when you are having 2 different atoms of different electronegativity, because one will be definitely having a tendency to attract electron, either A or B, and the other one will be having a tendency to lose the electron. But this is not the case when you are having a homonuclear diatomic molecule. In this case, both atoms will be having the same electronegativity, so they will cleave in such a manner that both of them get an equal share. Now, these are some of for that reason, you can actually rule out the possibility for option D and option C. That is because in both these options, you are having 2 different atoms bonded together. Okay. Now, when you consider the bond cleavage, always the bond cleavage or homolytic fission will take place only if the free radical that is formed as a result of cleavage. That is when this bond is undergoing a homolytic cleavage, it leads to the formation of two different free radicals. That is a free radical. This is possible only if this a free radical is stable. Otherwise, that fission is not favored. So the fission will be favored only when you are having a stable radical species that is being generated. Okay, only when you are having a stable species that is being generated. Now this is some point regarding homolytic fission. That is when you consider these two compounds, this is water and this is methane. Now when you consider the cleavage of hydrogen oxygen and hydrogen carbon bond in water and methane respectively, the product that you will get is hydrogen free radical and then hydroxide free radical. Then here also you are getting a hydrogen free radical and a methyl free radical. When you consider the energy for the cleavage of this bond, normally we expect the a lower bond cleavage or the lower bond dissociation energy for H2O, because we'll actually assume that this H plus and OH plus, H dot and OH dot is quite stable, so it will be having lower bond dissociation energy. But unfortunately, this water molecule, it has got a higher bond dissociation energy. That means that whenever you are having a very high bond dissociation energy, then it means that radical stability decreases. That is, when the radicals are having less stability, it means that it is very difficult to break that bond, because that is not favored, because if that bond break, it leads to the formation of less stable free radicals. So that is not favored, so it will be having very high bond dissociation energy. So from these two examples, one thing is clear: a methyl radical, or the radical in which the unpaired electron is present in carbon atom, is more stable compared to the case where the unpaired electron is present on an oxygen atom, which is more electronegative compared to carbon. So therefore, as a general point, we can say that radical stability decreases from left to right along the periodic table. So when you move from left to right of the periodic table, radical stability decreases. That is because when you move from left to right of the periodic table, the electronegativity of the atom increases. Therefore, it has got it cannot hold that unpaired electron for a long time. So therefore, the radical stability decreases. So when you consider the stability for these atoms, a carbon free radical is more stable compared to a nitrogen, which is more stable compared to an oxygen, which is more stable compared to fluoride. Okay, so this is the generalization that we obtain from the bond dissociation energy value. And some other factor which actually determines the stability of free radical is that when you consider the alkyl free radical, the stability is same as that of carbocation. That is, in the case of carbocation, tertiary is the most stable. The same is the case with free radical. In the case of free radical, methyl is less stable compared to primary, which is less stable compared to secondary. Which is more stable compared to secondary, and primary is less stable compared to secondary, and secondary is less stable compared to tertiary. Or in other words, you have to say that the tertiary is more stable. And another factor which increases the stability of a free radical is the phenomenon of resonance. If resonance is possible, that can increase the stability. And similarly, when you are having an atom with a lone pair adjacent to the free radical, that can also stabilize the free radical. And when the electronegativity, it is having an inverse effect. When electronegativity of the atom increases, stability will decrease. And therefore, when we move from left to right of the periodic table, radical stability decreases. And when we move down the group, that is down the periodic table or down the group, free radical stability will increase. That is because the electronegativity will decrease. And Moreover, another factor is the hybridization. That is, when you move from sp3 to sp2 to sp, the radical stability will decrease. That is because when the hybridization is moved from sp3 to sp2 to sp, it becomes more electronegative. And we have already mentioned that when the atom becomes more electronegative, the radical stability will decrease. Another point is electron withdrawing group. They will destabilize the radical. That is, when you are having electron withdrawing group adjacent to the free radical, that is a destabilizing factor, or stability decreases. So from these discussion, we can rule out these two options. So now we'll have a comparison of option A and B. And from this point, that is when you move from left to right of the periodic table, the radical stability decreases. Therefore, when you compare carbon and oxygen, oxygen is more electronegative. So O dot will be less stable compared to C dot. So most probably the answer will be option A. But in the key it is given as B. I think there is some error in the key that is given. Maybe they will correct it in the final answer key. So according to all these discussion, I feel that option A is the correct one. Okay. So the next question for this video is something which is related to the UV spectroscopy or electronic spectroscopy. And the question goes like this: which type of electronic transition can be seen in saturated aldehyde and ketone? That is, in saturated aldehydes and ketone, which type of electronic transition can be seen? Okay. So in order to answer this question, we need to understand the different types of electronic transition that is possible in electronic spectroscopy, as well as in which molecules these transitions are found. Okay, so when you look at the right hand side, you can see energy level diagram. This diagram represents the various energy level like sigma, pi, non-bonding, pi star and sigma star orbital. So this is the sigma orbital, this is the pi orbital, this is the non-bonding orbital, this is the pi star and sigma star orbitals, which are anti-bonding in nature. So when you consider the different types of transition in UV spectroscopy, the different types of transition is N to pi star transition, N to sigma star transition, pi to pi star transition, and sigma to sigma star transition. So these are the four different types of electronic transition that is possible in organic compound. Now when you consider each transitions in detail, we'll have a look at the compounds which can give these type of transition. For example, we'll consider the first transition, which is known as the sigma to sigma star transition. So from the figure you can see that it is the transition which is having highest energy. Okay, so before moving on to the this particular thing, we'll have a discussion regarding the order of energy levels. Order of different electronic transitions. So when you look at the figure, it is quite clear that sigma to sigma star transition is the one which is having higher energy. After that, when you consider, there are two different types of transition, pi to pi star and N to sigma star. Okay, so among these two transitions, the N to sigma star transition will be having the highest energy. Okay, N to sigma star will be having the highest energy. Therefore, we can say that the N to pi star transition will have the less energy compared to N to sigma star. And the least energy transition is N to So I've made a mistake here. It is not N to pi star, it is pi to pi star. Because from the figure you can see that pi to pi star and N to sigma stars are somewhat similar transition. And the least energy transition is N to pi star. So this is the energy order for various type of electronic transition. Now we'll have a look at the different types of transition in detail and in which compound these are possible. When you consider sigma to sigma star transition, this type of transition is possible in saturated hydrocarbon. That is normally when you are having compound which contains only single bond. For example, if you consider ethane, propane, etc. These compounds, they contain only single bond. So those compounds which contain only single bond or saturated bond, they will give rise to sigma to sigma star transition. Okay, now coming to the next transition, which is N to sigma star. N to sigma star are seen in compound which contain non-bonding electron. That is, for example, if you consider alcohol, alkyl, halide, etc. You can see that there is lone pair of electrons on halogen and oxygen atom. So these compounds, they usually exhibit N to pi star transition. So for N to pi star transition, in order to have N to pi star transition, it should possess a carbon heteroatom bond, most probably single bond, so that this heteroatom should also contain lone pair of electron. So in that case, you can get this N to sigma star transition. Now coming to the next type of transition, which is pi to pi star, and this type of transition usually occurs in compound which contain double or triple bond or unsaturated compound. Okay, for example, if you consider alkene like ethene or acetylene, triple bond, you can see these pi to pi star transition, and it is also possible in conjugated systems like 1,2-butadiene. Here also you are having double bond, therefore this pi to pi star transition is possible. Now coming to the last type, which is N to pi star transition. These are transitions which are which occur in compound containing non-bonding electrons on heteroatom. That is, this is somewhat similar to N to sigma star, but the difference is that in the case of N to sigma star, you are having a single bond between the carbon and the heteroatom. But in the case of N to pi star transition, you will be having a double bond like carbonyl group, and similarly in nitro group, etc. and cyano group. In these cases, you can have this type of N to pi star transition. Okay, so these are some of the examples. So I think you have got an idea regarding the various types of electronic transition. Now we'll go back to the question. So in the question, we are asked to find out the type of electronic transition that is possible for saturated aldehyde and ketone. So when you consider saturated, they have specified the word saturated in order to make you understand that there is no double or triple bond. Okay, so we can rule out the possibility for pi to pi star transition. And in carbonyl compound and in ketone, you are having a common functionality, which is a carbonyl functionality. So this is aldehyde, this one is aldehyde, and this is ketone. In both the cases, you are having a C double bond O. So we have already seen that in C double bond O, the type of transition that is possible is N to pi star. Okay, N to pi star transition is the one which is possible. And therefore, we can say that this cannot be the answer, because pi to pi star is not possible because it is a saturated system. And therefore, N to pi star, that is option A, is the correct answer. But here I would like to mention a point that normally in carbonyl compound, we can actually get two different types of transition. Definitely the N to pi star transition is possible, but along with that, sometimes you can also get N to sigma star transition, because if you consider the C double bond O group, it is actually C double bond O, but it has got the property to undergo resonance. That is, when you are having this type of functional group, this can undergo delocalization to more negative oxygen atoms. So we'll be getting a functional group like CO single bond. So when you are having the CO single bond, there is also the possibility for N2 sigma star. So in some cases, you will be provided with option where where you will be given both N2 pi star and N2 sigma star, and in that case you have to opt for that particular option. If it is not there, then you have to opt for the option containing N2 pi star. Okay, that's all for this question. Now the next question is a pretty simple question. It is about stereochemistry of a compound. A compound has been given which is E1 bromo 1 chloropropene, and you are asked to find out whether which groups are on the same side or on the opposite side. So you have to find out the correct answer from these options. So when you look at the structure of E1 bromo 1 chloropropane, how do you write the structure? So this is the parent compound. That is, it is a derivative of propene. So propene is a derivative of propane. So you have three different carbon atom, and it is propene. So one of the bond is a double bond. Now you have to balance the structure with hydrogen atom. Now this is the structure of propene. So you have to always number in such a manner that the double bond get the lowest number. So this is the structure and numbering of propene. So in the case, in the question, it is given in the one position, that is in carbon number 1, you are having a bromo group as well as a chloro group. So in that case, you have to replace this hydrogen atom with a bromine as well as a chlorine. So the structure will be like CBr, Cl, CH, CH3. So this is the structure of the compound that is being given. But the stereochemistry is E. Okay, so here you have a double bond, E. So E represents a structure in which the groups with same priority are on the opposite side. So initially you have to write the double bond. This is 1, this is 2. This is 1, this is 2. In 1 you are having two substituents which are bromine and chlorine, and in 2 you are having two substituent which is hydrogen atom and methyl group. So since it is a E compound, that is compound with E stereochemistry, initially before assigning the position of CH3 and H, you have to give the priority order for the substituent of the first carbon. That is, bromine is the one which is having highest molecular weight, that will be getting the highest priority. 2 is having the second, chlorine is having the second priority. Therefore, for this molecule to have an E configuration, in the second carbon atom you are having a hydrogen and a methyl group. Definitely methyl group will be the one which is having highest priority. So here the highest priority group is on this side. Therefore, in order to make an E compound, the highest priority group, that is CH3, should be on this side. Okay, and hydrogen should be on this side. So now when you assign the priority, it is like 1, 2. Now you can see that 1 and 1 are opposite, 2 and 2 are opposite. So definitely the stereochemistry is E. The designation for this compound is E. It is an E isomer. Now when you look at the structure of this compound, you can see, now we will go through the different option. Option A is CH3 and chlorine are on the same side. Yeah, that is correct. CH3 and Cl are on the same side. Now, CH3 and Cl are on the opposite side. That is not correct. They are on the same side. Bromine and hydrogen are on opposite side. No, that is not true, because bromine and hydrogen are on the same side. Now, chlorine and hydrogen are on the same side. That is also not correct, because chlorine and hydrogen are opposite. Therefore, the correct answer for this question is option A, with methyl and chlorine group on the same side. Okay, so that is a pretty simple question. So this is actually the structure of E1 bromo 1 chloropropene. Okay. The next question for the video is the one which is having some error. So I'm not working it out, because in order to assign an RS notation for a structure, you need to have that structure, but it is only the name is given. So for this name you can have different types of structures. So we cannot get the correct answer. There will be more than one correct answer in the option. Therefore, I am skipping this question. I think this question will be deleted for some reason. This is a pretty simple question, but it is not from organic chemistry, but I have included in this video because it comes in between some organic question. So it is about a question from the chapter mole concept. That is where you learn about molarity, molality, etc. The various expression for various methods for expressing the concentration of a solution. So in this in this question, it is given that you are having an aqueous solution of oxalic acid. And in the question there is a typo, that is, it is given as dehydrate, but it is actually not dehydrate, it is dihydrate. Oxalic acid is available as oxalic acid dihydrate crystal, and 6.3 gram of that is taken in a and it is made up to 250 ml. So the volume for the solution is 250 ml. So this is the weight of oxalic acid, and you also have the molecular weight for oxalic acid that you can calculate, and the volume is 250 ml. So that from this you can actually calculate the concentration of oxalic acid, or molarity of, or normality of oxalic acid. Now when you come to the second part of the question, it is given that we are actually titrating this oxalic acid against 0.1 normal NaOH. So how much of NaOH will be required to completely neutralize 10 ml of the solution? That is, we have initially made an oxalic acid solution and 10 ml of it is taken, and how much volume of NaOH, that is 0.1 normal NaOH, will be required to completely neutralize the solution. That is what is given in the question. So we have to find out the volume of NaOH which is required for the neutralization. Now we'll see that oxalic acid, when you look at the structure of oxalic acid, I think you are familiar with the structure of oxalic acid. Oxalic acid is a dibasic acid. This is the structure. And this is dihydrate, means there are two molecules of H2O along with this. So when you calculate the molecular weight of this compound, it comes around 126. Okay. So this is having two protons. You can see that there are two protons. So when you calculate the normality, you have to divide it by 2. Okay, you have to divide the normality by 2. That is not, you have to take the equivalent weight. That is, equivalent weight will be equal to, normality is usually calculated using equivalent weight. So before that I will write down the formula for normality. Normality is equal to weight into 1000 by equivalent weight into volume. These are in ml. So equivalent, when you find out, molecular weight is 126 gram, equivalent weight is equal to 126 by 2, because when you consider oxalic acid, the basicity is actually 2. There are 2 protons, therefore you have to divide the molecular weight by 2. Now when you substitute this value, the 2 will, this is the place where you substitute equivalent weight. Equivalent weight is 126 by 2, so 2 comes in the numerator. So weight is 6.3 into 2 into 1000 by 126 into 250. So this is how you find out the normality. So it comes around 0.4 normal. Now in order to find out the volume of 0.1 normal NaOH required to neutralize the solution, we can make use of the famous equation, that is V1N1 equal to V2N2. So V1 corresponds to oxalic acid, 1 corresponds to oxalic acid, and 2 correspond to NaOH. So we have taken 0.4 molar normal oxalic acid solution and 10 ml of it is taken, and in order to neutralize this one, how much volume of 0.1 normal NaOH is required. So when you find out X, it comes like 0.4 into 10 by 0.1. So it comes around 40 ml. Okay, so this is the answer. The answer for this question is option C. So this is a pretty simple question that you normally perform these calculations in your titrations. When you carry out volumetric titration, this equation is actually involved in the calculation of the normality of the given solution. So the next question is about a named reaction, which is known as the Woods reaction. And you are asked to find out the product of Woods reaction between two alkyl halides, which is alkyl iodide. One is ethyl iodide and normal propyl iodide. So in order to answer this question, you need to have an idea regarding what is a Woods reaction. Woods reaction is actually, it was a reaction that was developed by Charles Adolph Woods. So the reaction is named after him. And it is actually a coupling reaction. What is a coupling reaction? Coupling reaction is a one in which one compound adds to the other. That is, you will be having either same or different type of compound, and both of them adds. So that is a coupling reaction. What reagent that you require for this? The coupling is actually between two alkyl halides, and you are using sodium metal in dry ether as the reagent. So you are using dry ether because when there is moisture, it can lead to some abnormal product and all. So you should be very particular that you should take dry ether. And sodium metal is acting as the reagent or the catalyst for this reaction. So this is the general representation for Woods reaction. You are having two alkyl halide and two sodium atom, and when they undergo Woods reaction, the R alkyl halide will combine to form RR. So in order to make you understand better, I'll write the expanded form. That is, you are having two alkyl halide with the sodium. Two sodium is also there. Okay, so this is two sodium atoms are there. So normally this will be eliminated. That is, this will be eliminated as two molecules of NaX, and R will join to form the product. So this is a coupling reaction between two alkyl halides. In the right hand side of the slide, you can see many examples. That is, this is the general representation. You are having methyl chloride. Both the methyl group will combine to form ethane. When you are having isopropyl group, both of them combine to form a higher member of alkane. And similarly, when you are having two different, so this is the general case where both the alkyl halides are same. But this is another case where you are having two different alkyl halides. So in that case, you can actually get many products, like mixture of product can be obtained. This R can combine, R dash can combine, and both R and R dash can combine. And that combination is also in different way it is possible. Either it can be an R dash combination or R dash R combination. So most probably you will be getting a mixture of three products. And similarly, the question that we have provided with is something like that. That is, we are having two different alkyl halides, ethyl iodide and propyl iodide. So we'll write the structure of these one. The first one is a ethyl iodide, and the second one is propyl iodide. Okay, these two are the structure. So when they combine, this can combine with itself. That is CH3, CH2, CH2, CH3. In that case, you will be getting normal butane. That is, two molecules of ethyl iodide can combine to form normal butane. Similarly, two molecules of propyl iodide can combine to form CH3, CH2, 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 CH3. So this can lead to normal hexane. There are 6 carbon atoms. So these are the product where the reactant undergo, one of the reactant undergo coupling with itself. Now you can also have the mixed product. That is, one molecule of ethane and one molecule of propane can combine to form CH3, CH2, 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 CH3. In this case, you will be getting a normal pentane. So 3 products are possible. So which is in the question it is given, you have to find out the compound which is not produced as a result of Wood's reaction. Normal butane you can actually get from Wood's reaction. Normal propane is actually not possible. Normal pentane is possible. Normal hexane is possible. Normal propane is not possible because you are provided with alkyl halide. You cannot get alkyl. You cannot get the alkane with a carbon atom, with the number of carbon atom less than the number of carbon atom in the starting material. So when you are having ethyl iodide, you can get ethyl iodide, the coupled product of ethyl iodide, but you cannot get methane because that will be having carbon atom less than the number of the one which is present in ethyl group. And similarly, when you are having propyl group, and moreover you cannot also get ethane. Ethane you cannot get, methane you cannot get. Similar is the case with normal propyl iodide. From normal propyl iodide you cannot create propane. You can create propane by some other method. By Wood's reaction, it is not possible. Actually, we are talking about Wood's reaction. Okay, so you cannot produce by Wood's reaction. You can only double the number or increase the number. You cannot reduce the number, or the number cannot remain the same also. So therefore, the answer to this question is definitely normal propane. Okay, so this is a simple reaction. It is very easy to understand as well. Now the last question for the video is about an organic reagent which is alcoholic KOH. What is the function of alcoholic KOH? Option A is dehydrogenation, dehalogenation, dehydration and dehydrohalogenation. So when you look at different options, dehydration means it is the removal of water. Sorry, dehydrogenation means it is removal of hydrogen. Removal of hydrogen is actually oxidation reaction. Okay, so there are different definitions for an oxidation reaction. Oxidation reaction can be addition of oxygen, removal of hydrogen, or removal of electron. All these come under the case of oxidation. So dehydrogenation means removal of hydrogen. D means it is a word which specifies removal. So dehydrogenation means removal of hydrogen. That is usually an oxidation reaction which is performed by oxidizing agents like potassium dichromate, potassium permanganate, etc. So that is not the option. Dehalogenation, that is removal of halogen, say X. Removal of halogen, any halogen may be removed as X or X2. So that is not the reagent. Alcoholic KOH is usually not used for dehalogenation. And similarly, dehydration means removal of water. So this is usually done with the help of concentrated sulfuric acid. Dehydrating agent like concentrated sulfuric acid. Alcoholic KOH is not used for that purpose. Therefore, this is also not the option. And dehydrohalogenation is the removal of HX. Can be HCl, HBr, HI, etc. And this is the correct option. The function of alcoholic KOH is removal of HX. And another point that you have to keep in mind is that you are also having another reagent which is known as aqueous KOH. So when you are using aqueous KOH, the function is different. The function is hydroxylation. Hydroxylation means addition of OH group. That is, you can convert it into alcohol. Okay, so these are the functions of alcoholic KOH. Alcoholic KOH is used for dehydrohalogenation, whereas aqueous KOH is used for hydroxidation. Okay, so that's the end of this question. That's all for this video, and I hope that this video will be useful to you, and thank you for watching. So if you like the video, please do subscribe and share. And again, I am reminding you about the coaching classes. If possible, you can join the class, and the number is given in the description box, because in YouTube videos it is very difficult to record the video, so I will not be able to complete many portions at a time. So if you are joining this course, it will be more useful. With a short period of time, you can grab more ideas regarding chemistry. So it's only a suggestion, and if you find this video useful, please suggest these videos to your friends as well. And see you soon with the next video. Thank you.